Good afternoon, everyone. Are you guys doing well? Probably you will you will get to know that I just finished grading the exams. So I'm going to post the results this afternoon. But before I have to make copies of the exams, and after I finish that, on Wednesday I'll give you the exams. For those of you that are here, just come on Wednesday. So I'm just going to give you personally the exam. And if you aren't here, I'm not going to give you the exam. But if you cannot make it, then stop by my office. I'll give you the exam too. So just to give you an idea, highest grade was 100, and there were like 3 or 4 hundreds. Lowest grade was 53, and the average was 85. And I'm going to publish all the results with a curve so you know where you are compared to the other people in the class. Do you guys know how Exxon works with employees and with how they reward how well they're doing?
Yes.
So how does it work, Ms. Godel?
It's a 3-tier system.
Okay. And?
Where at the end of every year, the managers and the
Yeah.
people in that CL group rank the people beneath them in 3 tiers.
Okay.
And then the frequency that you get a raise is based on which percentile you were.
Okay, but that's not the end of the story, right? Also, you're ranked the lowest.
Oh, yeah.
Probably you will not make it the next year. So this is just the first midterm. There is a chance to make it up. There is a chance to make it up with midterms, with the final exam, with homework, participating in class. So if you didn't do that well this time, there is still time to make it up, okay? But many of you did very well, and I'm happy for that. There were some common mistakes. I will talk about that on Wednesday. All right, but we'll talk a little bit more about the exam on Wednesday. Today, we'll continue talking about faults. All right, so let me get rid of this. And let me make sure I'm recording. Yeah, this is good. All right, so just as a reminder, we have been working with analyzing and better understanding how faults form, and if you were to change the stresses or pressure, if they were to reactivate or slip again. And this is very important because many times when these faults are close to failure, they are more likely to be hydraulically conductive. So the permeability of the fault is going to be linked to what the state of the stress is. If you have a fault that is currently moving very slowly but moving, it's very likely that fault also is going to conduct fluids through it. If you have a fault that is static and it's not moving, and probably there is clay in here inside the fault, probably that's going to be a sealing fault. But stresses are going to be a big part of that mechanism of getting to know if the faults are conductive or not. And we learned the geology part, we learned about the strength of the faults, and now we're here trying to understand, according to each faulting regime or each stress regime, which of the faults are going to be more likely to form or more likely to reactivate. And we saw the case of the normal faulting. When you have normal faulting, because maximum stress is vertical, minimum is horizontal, in this particular case is in this direction, the faults more likely to reactivate are going to be steep, and they're going to have a strike perpendicular to the minimum principal stress. And this is how these look in the Stereonet map, and this is how the Mohr circle looks. And today we'll talk a little bit more about the Mohr circle, so don't worry about that for now. The important part here is to identify very quickly what would be the plane of maximum shear to normal stress, which is equivalent to say, which is a plane in which you will have a fault, or in which it's going to be most likely that if a fault already exists, that it reactivates. And this is the case in normal faulting. For strike slip, it's exactly the same thing, but now the plane of maximum stress is horizontal. The stress in the horizontal direction, and the plane applied on that maximum horizontal stress is going to be this one. And the faults are going to be most likely to reactivate or form are going to be steep planes with respect to this plane. And the same rule holds, and the angle beta is going to be this one. So for these two faults, 1 and 2, we measure this strike and dip. Notice that if this is beta, if this is 90 degrees, and if beta is 60, this angle has to be 30 degrees. And that's why we have 30 degrees from the north to the west, 30 degrees from the north to the east. And the dip is going to be 90 degrees. So notice that this angle beta, it's always like the same when you follow this rule that it's the angle between the plane of the maximum stress to the plane of the fault. But depending on which stress regime you are, it's going to mean different things. Here it means dip. Here it means or affects strike, not dip. All right, so let's continue with this characterization, and we're going to put here the Stereonet map. Remember, this is the north. This is 90 degrees, 60 degrees, 30 degrees, and 0. So the plane number 1, I'm going to use my graphical tool. And number 1, it's this one. It's right there. And it has a strike of 30 degrees. So the tip is going to be pointing right here. Remember, always the point is not the strike of the plane. It's normal to the plane, what you put. And because in this particular case, it is 90 degrees, and there is no way to tell if either I have this case or I have that case. So in these cases, what we do, then we just draw 2 points. So number 1 could be either here or there. And number 3, number 2 is going to be this one. And I'm going to, so something like this. So it's going to be either here or either there. And this one is going to be number 2. Deep 90 degrees, the point is on the outer edge of this Stereonet projection. In the 3D Mohr circle, the biggest Mohr circle is going to be the Mohr circle that includes the minimum horizontal stress and the minimum and the maximum horizontal stress, so sigma h min, sigma h max, and let's assume that somewhere over here we have sigma b. We're going to have tiny circles in between, and points 1 and 2 are over here at the limit of failure. And if I chose the center of the biggest circle, this angle will be 2 beta. We'll talk a little bit more about that later on, don't worry. All right. And finally, let's go to the third case. The third case is reverse faulting, and in this case, the most likely shear plane, what do you think is going to be? Well, first of all, which is in which direction I have the maximum stress in reverse faulting? SH max, and the minimum is SV. Very well. So let's imagine that we have SH max in this direction. This is going to be the plane of the maximum stress. Let's say that we have SH mean in this direction, and SV the lowest in this one. Now you have to be able to see where is going to be the plane of the maximum stress. Remember, the rule is going to be that that plane or the fault as it moves is always going to push against the minimum principal stress, which in this case is SV. So if a wedge were to form in here, it will push against SV and it will go in the direction of SH max. All right, so before I make the drawing, what do you think is going to be the strike of such fault? 90 degrees, very well. It's going to be 90 degrees because it's going to be, let me do one over here. Let's say that starts somewhere over there, and as you push in the direction of SH max, it forms like a plane going in this direction. I should do that with colors. Do you guys have any fun story from the weekend? No one? What? No? It's a tough game. Did UT win or not? Yeah. Yeah. But how many points? 2 points? Okay. Good. So who is the first one in the conference then? OU? Okay, still OU. All right, so this one is going to be number 1. And as you see, as you push in direction of SH max, and this one moves against SV with an angle here, beta, well, remember beta for this particular example is 60 degrees. This is what is going to happen. And the strike is going to be 90 degrees, or what is the same, the strike is a little bit different. We could say also the strike is in east-west direction. And for another one, let's say we were pushed from the back, probably we could have another fault, which is the conjugate of that one, and it goes in this direction. You cannot see in the back, but the strike is the same. And what is going to be the dip of such fault? Let's say of number 1. So you know what beta is. Beta is 60. This is going to be an angle of 90 degrees. Therefore, this is going to be the dip. And the dip is going to be, in this particular case, 30 degrees, very well. And 30 degrees to the south or to the north for this particular case? South. And this one is 30 degrees to the north. So this is everything you need to know about the ideal orientation of this type of faults and how to calculate strike and dip. You may try the same exercise, but with a friction angle, let's say, of 40 degrees, or with a friction angle of 25 degrees. And what you are going to see that in this case, what is going to change is going to be the dip. In this case, it's going to change the strike, and this one is going to change the dip. You could also have SH mean in another direction other than east-west. It could be direction north-south, or it could be at any angle. And we'll talk a little bit more about this at any angle later on when we talk about the homework. But when it is at an angle which is not 0 or 90, it gets slightly more difficult. But if you apply the same principle, it's not difficult to solve. All right, so let's just complete the picture for now. Stereonet. And again, this is 30 degrees, 60 degrees, 90 degrees deep. And this is the first fault. Number 1 is dipping towards the south, 30 degrees. So it's something like this. It's going to be a point right here, number 1. And number 2 is going to be the opposite, something like that. And it's going to be right there. And the 3D Mohr circle now is going to involve sigma H max and sigma V, where sigma V is the smallest. So let's say sigma V somewhere over here, and sigma H max somewhere over here. And the 2 points are here, 1 and 2. And if this is the center, this is the angle beta. 2 beta, sorry. Okay. So I think we're done with these 3 examples. Do you have any question about these 3 examples? Remember, what we're trying to see is to find the plane of maximum shear to normal stress ratio. All these points, they share in common that is the maximum ratio of shear stress to effective normal stress. And at that point is where you are going to happen shear failure. There are always 2 solutions for this case. And in normal faulting, they give you different dips. In a strike slip, they give you different strikes. And in reverse faulting, they give you also different dips. For example, for this case of normal faulting with same strike and different dip is what you can see in this map. You see that in some directions, probably later if you get closer, there is a little thing that points in the direction of the dip. So, for example, in this case, that a little thing is pointing in this direction, and in the other one in this direction. So that means 2 normal faults are going like this. It's the same state of stress. It's just a fault that one goes in this direction, another one goes in this direction. And what it is in the middle is called a graben. And I believe I have an example of strike slip as well. Let me see if I find it. Okay. Yeah, this one. All right. Let me tell you what you see over here, and then I'm going to ask you a question. What you see here is a seismic image of the top of a reservoir structure in the Middle East. The color indicates the depth. So red is shallower, blue is deeper. And this is an anticline structure. So this is something like this, right? Going like that. If we have an anticline structure, that means that there was some folding and there was probably some stress that pushed it in this direction. All right? So you all have a mental idea about what's going on in here? All right. So let's add now the part of the fracturing. These lines that you see over here are parts of that reservoir structure that you have some little ridges because the rock failed. It folded, but sometimes it was too much folding and it failed in planes that are following the mouse in this direction, but also in this direction. So it is, let me see how I can do to just make this clear. It's like this. So the thicker lines are planes like that, and the other ones are planes like this. Okay, so for extra points, can anyone tell me what was the stress regime that caused this type of faults? What? I heard something. What? I didn't hear. No. No. Strike slip. But I didn't hear very clearly from which of you came. So next time you raise your hand, and then as you have the question. It is a strike slip, okay? Okay, tell me now approximately, if this is strike slip, then what is the azimuth of SH max? And what I mean with azimuth SH max, the angle between the north and the direction of SH max. If it's going this way, this will be 0, this will be 90, let's say this will be 45. All right, so what is the azimuth of SH max? Who said 90? Okay, Mr. Dodd here, and you say that as well. Why? Let's go, Mr. Dodd, you go first.
The orientation of the strike.
And where should SH max be? Do you agree with that, Daniel?
Yes.
So, you don't agree with that? Well, why not? Because it's wrong, but why is it wrong?
It's tilted a little bit, so it's more like 60 instead of 90.
So how much would you say?
I would say about 57.
57.
Yeah.
I think you're looking at the strike of the fault, but that's not what I'm asking here. I'm asking about in which direction SH max is. So for this particular case, if these are the faults, let me move this down a little bit so I can get to that. All right, so this is one fault, and actually it's a plane, right? So let me use this. If this is a fault like this, and this is what you're seeing here with those lines, and this is a fault like that, that means that SH max is going exactly in the middle of those. So the direction between the north and SH max is about, in this case, 90, let's say 95 degrees, is exactly in the middle. Do you see that? Does everyone see that? That's the case? So this is exactly the same. Let me here share that the image. So this is what we have over here, and in this case will be something. I don't know if I can make it, but this is the direction of SH max, right? And in the image is coming here from the north. Notice that SH max goes in between the strike of the two lines. And if you, it's the same thing with normal and reverse. The maximum stress, for example, goes in between those two planes. And here is the same. The maximum stress goes in between those two. But for strike slip, it happens to be that you do have that affects strike, not tip. So it's a little bit clearer to see what is the direction of SH max. All right, so let me assign the extra points, and we'll continue. Do you guys have any question about this? I like these kind of examples that showing you some field data, so you have to interpret that based on the fundamental knowledge that you should know. So if you don't understand this example, please let me know. Okay. I can't find you, Daniel. Can you remind me your last name? Kim. Okay. Oh. Over here, you don't have a beard and a mustache, so I'm going to do it. I'm going to draw it on top of you, and then I'm going to recognize you now. All right. Okay, good. And since we are here, let me show you another example that we said that we'll talk in the problems. All right, now let's come back to this case. Again, for some extra points. People other than Mr. Dodd and Mr. Dohium, tell me, I'm going to tell you that these are faults and they have a steep angle. And the lines are the strike of the faults. What is the direction of SH mean? Please raise your hand so I know that you want to participate. You want another chance? Okay, so what is that direction of SH mean? And I mean the angle. Let's talk a little bit more specifically. The azimuth, the angle between the north and the direction of SH mean.
This one's got to be 9 degrees.
9 degrees? No, I'm sorry, but that's not a mystical deal.
It's 135 north.
Something like that, right? So in this case, the faults are these planes. No, it's not straight. It's at the tip. It's something like this. Something like that. So this is like that. Those are those lines. Here you just see the strike. And this is the direction of SH mean. The faults go in this direction, and SH mean is in this direction. This is normal faulting. This is in Eagle Ford Shale. So SH mean goes in this direction. And if you check in maps about drilling surveys, you will see that also wellbores go in this direction for laterals and fracturing. Yeah.
Can you explain one more time why it's normal faulting?
Well, in this case, I know it is normal faulting,
Oh, okay.
but also I see that the lines of the strike are very consistent. So, for example, if we had a strike slip, probably we'll see stuff like this. Right? This could happen also with reverse faulting, okay? Right. But I also told you that this was like, these faults were relatively steep.
Oh, okay.
So that's, and we know this is a normal faulting because it's in the Eagle Ford
Okay, so
plate.
that's why you reduce the
Yeah.
possibility of
Yeah.
So in
Yeah.
normal faulting, it's like perpendicular. The SH mean is perpendicular. to the
Yes.
striker.
Yes.
And are the
Correct.
two, are they in the same direction?
Well, let's take a look at this. Okay, let me bring the map. All right, here we're looking at the first case. And in the first case, SH mean is going in direction of 145 degrees, and the strike is perpendicular to the direction of SH mean. This just holds for normal faulting, okay? If you were to have reverse faulting, the direction of SH max will tend to be perpendicular to the strike of the faults will tend to be perpendicular to SH max. And if we want to see a last example about reverse faulting, you just can look at some mountain building, and you see that usually where are we? That usually you have mountains, for example here, which are perpendicular to the direction of SH max, which in this case, for example, is east-west. If you were to go somewhere over here, direction of SH max goes in this direction, so the line of the mountains is telling you more or less where those faults are forming, perpendicular to SH max. So the strike of the fault will be perpendicular to SH max.
Oh, so like a mountain line is the strike?
Yeah, in this case it tells you more or less a strike. All right, okay, let's see what time it is. It's we need to talk about the 3D Mohr circle, guys. All right. So probably you remembered the Mohr circle from previous classes. But now we'll get to talk about the 3D Mohr circle and its applications. All right. So let's imagine a hypothetical 3D Mohr circle. We'll start with the case of normal faulting, but the same applies for any other stress regime. We have three stresses which are not the same, which are all different, because all of these are stresses which are on the x-axis. That means that these are principal stresses, because shear is 0 at all these points. All right. So let's see what is the meaning of this. First of all, we know the Mohr circle in 2 dimensions. And if we link the maximum stress and the minimum stress, we'll get that circle. That circle is going to have a center. Let's call it center number 1. And now let's see what that means. We're going to make a block diagram of the subsurface. And here I'm going to place sigma h mean in this direction. This is just an example. I'm making it up. It could be in any other direction. And this is sigma b. All right. As you can see, this point is this plane, right? So this plane is that point. And the stress, state of stress on this other plane is this point over here. The circle that goes from here to there means all the possible state of stresses in this circle when this is an angle two times beta 1 going from this plane to that plane. So if this is 2 beta 1, that means that this is beta 1. And basically, every point in the circle is going to be a plane over here. And according to what is the value of the angle, I will get to know what is the stress at that point. For example, if beta 1 were to be 45 degrees, that would be a point right here. And this would be a line somewhere over here and a plane somewhere over there. But what you have to notice here that now we are in 3 dimensions, okay? And that adds a little bit more complexity. Beta 1 is the angle that goes from the angle of the maximum stress in this case, which is sigma v, to the plane of sigma h mean. But it's also respecting like this line. You should think about this line as sort of a hinge that on which this plane moves. This is not just a line over here. This one is a plane. And it's hinging on that hinge. And always that strike is the same. And that's where the three-dimensional component comes into the picture. When beta 1 is equal to 90 degrees, you go all the way over here and you get to sigma h mean. So at this point, if I told you, for example, tell me what is the shear stress and normal stress for a point somewhere over here, given the strike and the dip, you are able to do that. Why? Because you know what is the center of this circle. Let me zoom out a little bit so I can write the equations. For example, center 1 is just sigma v plus sigma h mean divided by 2. Radius number 1 is sigma v minus sigma h mean divided by 2. And in this particular case, any state of stress, sigma n, is going to be equal to the center plus the component in this direction, and that's going to be R1 times trigonometry, cosine or sine of 2 beta 1. I'm looking for this additional amount in order to get here, cosine. Most of you did calculate correctly the true vertical depth in the third problem, but some of you didn't, okay? If you don't remember trigonometry, you should try to refresh that. All right, that's going to be sigma n, and tau is going to be just R1 times the sine of 2 beta 1. Notice that when 2 beta 1 is higher than 90 degrees, it's going to be a negative value. And one sec. And then instead of adding something, you're going to subtract that, and it's going to be somewhere over here. Yes? What? Yes. So, okay, then I'm looking at this circle. This is C1, this is R1, this angle is 2 beta 1, And the equations that we get are going to be those two.
Wouldn't the center be that plus sigma h min?
Center will be sigma v plus sigma h min divided by 2. What is the issue?
Wouldn't that be assuming that sigma h min starts at is 0?
No.
Okay.
No, because it's just the average between these two numbers, so that's going to be
Oh, okay.
the
Yeah,
center.
I
Or
was thinking about it differently. Never mind.
yeah, the center of the circle is just going to be the average of those two. The radius is going to be the difference divided by 2.
Yeah, thank you.
Okay, so again, here are the equations, but this is just saying it's just trigonometry. We want to know what is sigma n and what is tau at that particular point. So now with this circle, we can get to know all the possible state of stresses from a plane that hinges from the plane of sigma v to the plane of sigma h min. And it's going to be exactly the same with the two other ones. So let's do this case. In between sigma v and sigma h max, there's going to be another Mohr circle, which is going to be that Mohr circle. It doesn't look that much like a circle, but I meant that to be a circle. And if we look at what that means in reality, it's the same cube. We have sigma v, we have sigma h min, and here we have sigma h max. Sigma v, the maximum, is this one. The plane of sigma h max is this other plane over here. And that circle is going to mean all the planes in between the plane of sigma v and the plane sigma h max with a hinge on that line. And let's say, for example, that the center C2 is this one. And let's say that we are looking at what would be the state of stress in that point. So this is going to be 2 beta 2. And the same thing, beta here is going to start increasing from the plane of sigma v. And therefore, this is going to be beta 2. When beta 2 is equal to 0, we are on the plane of sigma v. When beta 2 is equal to 90 degrees, we're in the plane of sigma h max. And everything in between is that plane. So again, now, if you had a fault with a strike of, in this case, 90 degrees, 0 degrees, then you could solve the state of stress for any fault with any dip. Because the equations, again, are relatively simple. Let me just complete this. C2 is going to be sigma v plus sigma h max divided by 2. R2 is going to be this. And sigma n tau for these particular cases is going to be C2 plus R2 cosine 2 times beta 2 R2 sine 2 beta 2. Remember, all these equations are also in my notes online. So if you don't have time to copy them all, you can check them over there. All right. So we know the state of stresses for all these planes. We know the state of stress for all these planes. And the last one is going to be let me find the center first. Center is going to be somewhere over here. And same thing as before. This is going to be 2 times beta 3. And now we're looking at, this is sigma v, sigma h min, sigma h max. Okay. Now we're in the circle that links sigma h min and sigma h max. So where is going to be the hinge now? Which line? This one, or that one? The last one, right? And where is beta 3 going to start increasing from? From this line, or from line number 1 or line number 2? Line number 1, right? So the hinge is on this one. Let's see, we did a beta 3, which is a little bit more than 45. So it's going to be this one. This is going to be beta 3. This is the plane of the maximum stress. This is the plane of the minimum stress. And notice that when I say with the maximum stress, I'm referring to this particular circle. For this particular circle, the maximum stress is sigma h max, and the minimum is sigma h min. It doesn't mean that for the entire block, this one is the maximum. But this is it. Now we can get to know, if we knew sigma h min, sigma h max, sigma v, with these simple equations, C3, R3, I'll let you complete that, sigma n, tau, you could tell me the stress anywhere with those angles. But if you notice, for these 3 planes, in every single case, the plane contains one of the stresses. In this case, the plane is in the direction of SH max. In this case, the plane is in the direction of sigma h min. And in this case, the plane is in the direction of sigma v. For example, in this case, it doesn't matter what the value of sigma v is. Your normal and shear stress just depends on sigma h min and sigma h max, which is that circle. And the question is, what happens when you have a plane which is not oriented in such a way that it contains the direction of one of those stresses? What is the stress on that plane going to be? And where in the Mohr circle is going to be? Okay, those planes are going to call oblique planes, and there is no chance that they are outside the biggest Mohr circle, because the principal stress cannot be higher than sigma v, or the normal stress cannot be higher than sigma v. So it cannot be here. The normal stress cannot be smaller than sigma h min, so it cannot be anywhere in here. Also, it cannot be anywhere inside here, because if I had, for example, a point somewhere over there, that means that this is a principal stress. But we already have 3 principal stresses, so it cannot be anywhere in here. And by extension, cannot be anywhere in there too. The oblique planes are going to be all the way over here, in between those 3 circles. And if you want to calculate what is going to be the stress on that particular plane, It's going to be a little bit more difficult, and we'll talk about that on Wednesday. All right? See you guys on Wednesday.